Hi, in this video, I'm going to discuss symmetries and how they lead to conservation rules, which govern what processes will and will not be allowed in particle physics. All right, so when we're studying particle physics, one of the ways that we better understand different particle interactions and the way particles interact is by thinking about what happens if we simply smash particles together, right? If we have particle collisions, or if we study the way particles decay and what particles come out when a particle ends its lifetime. So, for instance, we might think about smashing two protons together like they do at the Large Hadron Collider. And you might ask, well, what types of things might come out if we smash two protons together? Well, we now know that a proton is made up of two up quarks and a down quark, as shown in this schematic diagram here. So if we smash two of these things together, you might have guessed, well, okay, we now know there are all of these different types of hadrons, which are made up of different combinations of quarks. So maybe the particles that are allowed to come out are particles that are made up of four up quarks and two down quarks, right? After all, those are the fundamental particles that we started with. And so maybe we can get some different sorts of hadrons out, but that's that with that quark content. Well, fortunately, or maybe fortunately, I guess it's a matter of opinion. Interestingly, certainly, uh, all sorts of different things can actually come out of this collision. And what we'll be doing in particle physics is calculating the probability for different types of things to come out. And they don't necessarily have to be limited to the four up quarks and two down quarks that you started with. In fact, if you smash these protons together with high enough energies, then some of that energy could be converted to mass. So you could actually end up with even more massive particles than those that you started with. So things actually are a lot more interesting in particle physics than you might have thought a priori. So is anything fair game, right? Are we just using E equals mc squared to check conservation of energy? Like what are the rules of the game here? Well, hopefully most of you have at least heard of Noether's theorem before. Noether's theorem teaches us that symmetries of your physical system are associated with conservation laws. So whenever you have a symmetry, you have a conservation law, and vice versa. If you have a conservation law, then there must be some symmetry that's associated with it. Not all the symmetries or conservation laws are going to be ones that are familiar necessarily, but some of them are quite familiar. So for example, we know that our quantum field theory is going to be Lorentz invariant. It's going to have Lorentz symmetries. So our particle physics are going to be governed by these Lorentz symmetries. So we have spatial invariance. We have spatial translation invariance, so translating in space. We have temporal translation invariance, which I mean by that moving forward and backwards in time, right? The laws of physics shouldn't change as we move forward and backwards in time. And we know we have rotational invariance. And so Noether's theorem teaches us that these symmetries of our system should have associated conservation laws. And these particular symmetries have conservation laws that are very familiar to us. So translation in space invariance is associated with conservation of momentum. Temporal translation in time, is associated with energy conservation. And then rotational invariance is associated with angular momentum conservation. So these aren't our only conservation laws. Some conservation laws are going to be very new to someone who's seeing particle physics for the first time. But one conservation law you might have heard of before or might think about is electric charge conservation. So you might wonder, what symmetry is this associated with? So this is actually going to be associated with phase invariance, which you may or may not know what I mean by that now. We'll definitely dive into it in future videos. But it's good to know that even things like electric charge conservation do have some associated symmetry. It's just going to perhaps be a new type of symmetry to you. And there are even more of these. And again, we'll get more into them in the future. But for now, sort of to summarize, when you're considering what processes are allowed in particle physics, so you're wondering what decays are allowed if I collide two particles together, what types of things potentially could come out. There are really 4 things you need to check to see if it's going to be an allowed process. So first, are energy and momentum conserved? That's going to be very, very important. If you have a particle which is decaying, for instance, it can't decay into something with more mass than it started with, right? You can't have, assuming we're imagining the decay starts at rest, right? If we go to the rest frame of the particle, there's no way to decay to something that's more massive than you started with. So you need to check things like that. Are energy and momentum conserved? Is electric charge going to be conserved? And then perhaps more new conservation principles, which are associated with symmetries of the standard model. First is that quark numbers are conserved, or this is one way we can think about this conservation law is by counting quark number. So if we associate to every quark a +1, and then every anti-quark a -1, then the total number you start with, if you add all of those numbers up, must equal the total number that you have in the end. Similarly, with leptons, we have lepton numbers. It's important to note, though, these are for each lepton family, right? Each lepton family here. So, and by that, an electron and the electron neutrino, those are in a lepton family. Muon neutrino, that's in a lepton family. So we've also used this word generation, right? So it's within each generation. We're going to have a lepton number. So, we'll have, you can consider the electron lepton number, muon lepton number, tau lepton number. And again, we're going to associate a +1 with the lepton, a -1 for anti-leptons. And if you add all those up, whatever you start with, you need to end up with. And if you follow these 4 basic rules, then you can start to discover what processes are potentially going to be allowed, which scattering processes or which decays are potentially allowed. And then what we're going to want to do in particle physics is calculate the probability for these different processes to occur. So some processes are going to be much more likely than others. Some will be possible, but are going to happen very rarely. But we'll want to consider all of those at the beginning, and then do the calculation to figure out which ones are going to be most likely. All right, so that's how we can relate symmetries of our system. So we really think of symmetries as a fundamental aspect of our system. And then from symmetries, we get conservation laws. From those conservation laws, we understand what types of processes are going to be allowed and which ones will just never happen because of these conservation laws.